Welcome back, guys. In this problem, we'll be analyzing a circuit involving more than one loop. And these problems tend to be a little tricky at times for students because the science can be confusing. So I'll be pretty careful in dealing with those things. Let's take a look at the problem statement. Two batteries are connected in a two-loop circuit with three resistors as shown in the figure. The circuit is grounded at point A. What is the voltage at point B? So in this circuit diagram, we have two different loops, and we're given all the voltages, we're given all the resistances. We're also told that at point A, the circuit is grounded, so that'll tell us that the voltage at that point is defined as 0. And what we're asked to find is the voltage at point B. And these multi-loop circuit diagrams typically are exercises in applying Kirchoff's laws many times. So let me first recall those laws. The first law states that the current coming into any junction must equal all the current leaving the junction. And I'll write that as the current into a node is another name for a junction, equals the current out of the node. And this is just a statement about the conservation of charge. All the charge that enters a node at any given time interval must equal all the charge leaving the node at that same given time interval. Otherwise, a charge must be created or destroyed, which does not happen. And then the second law is, or states that if you take any loop, any closed loop inside of this circuit, then all the voltage differences across all the elements added up must be 0. So for example, if you add voltage across a battery, you must drop it across a resistor, and then adding up and subtracting all those voltage differences, you're going to just get back to 0. Now in applying these laws, the first thing we should always do is label the current directions in the diagram itself. And sometimes it may not be obvious which direction the current is flowing, especially if you have more than one battery. But it's not really that important. If you get it wrong, you just get a negative for the answer. So you still want to try to label them in the right direction. So if I take a look at this left loop here, the battery it has a low voltage here and a high voltage here, which indicates that it's going to push the current in this direction. And so I'll draw this direction for this current here, which I'll label as I1. And one thing that often confuses students is when do you have to add more current? So for example, this entire branch here, at no point in this branch, or at no point in this wire here does it branch off into two. So this is all current I1. Only when you get to a node where it has to branch do you have to start labeling different currents. So at this point you're going to have another current going down and one going that way, which are distinct from I1. And so I'll label this one I2. I'll just label it going down. Again, it's not critical if it's right or wrong for the direction. And then I'll label this direction going I3. And then if you follow the loop around over here, this is all I3 because it's not branching anywhere else. So we've labeled all the possible currents in this situation. And now let's apply Kirchoff's law. So the first one I always apply is the junction law. And so what that's saying is at any given node, the current coming in must equal the current leaving. And so I'll pick node B. The current coming in is I1. The current leaving is I2 plus I3 because those are both pointing away from the node. So that equation reads I1 equals I2 plus I3. Current in equals the current out. And now when you want to apply Kirchoff's loop rule, you have to first define which direction your loop is pointing in. You can choose either clockwise or counterclockwise, and that direction is not critical. It doesn't really matter which way you do it, but you do have to write it down just so you're clear on which way you're moving. And so I'll choose clockwise at both of these guys, and I'll choose this loop and this loop. Another choice would be this loop and then the big loop. It doesn't really matter. You can choose only two here because the third one is a linear combination. So we only have two distinct choices, and I'll choose the left inside and the right inside. And I'll choose clockwise here and clockwise here. Now once you've drawn that loop down, you can actually go through the circuit elements one by one and adding up all the voltages. So I'll do that next for the left loop. And I always start, this is just the way I do it, I always start right at the lower voltage of the battery. And so the first number I'm going to have is if I start here, you add voltage across the battery that direction. Notice I'm going the direction of the loop. I add voltage across this way because I'm going from a low to a high voltage based on the way the circuit element is drawn. So it's plus epsilon 1. And then continuing around the loop, once I get to this point right here, I'm going to drop voltage across the resistor as long as my loop is pointing in the same direction as the current that I've drawn. This is why it's important to draw these directions. So because the loop is going in this direction and the currents are pointing in the other direction, I'm going to lose voltage here. So it's going to be minus the voltage drop across the resistor, which equals the, by Ohm's law, it equals IR. So it's minus I1 times R1. And then continuing around the loop, I'm going to finish the loop up over here. You're going to again drop voltage because the current direction is the same as the loop direction, so it's minus I2 R2. And we're back to where we started, so that equals 0 by Kirchoff's loop law. Okay, so that's that loop, and then for the right one, I'll have you guys doing your own. Do the exact same thing I did here. Be careful of your signs. Pause the video now if you need to, and we'll come back and take a look. So the equation you should get for this loop is the following. Epsilon 2 plus I2 R2 minus I3 R3 equals 0. Now, there's a positive sign here because the loop is going in this direction. And on this branch, it means it's going upward, but the current is pointing down. Because they're pointing in opposite directions, it's going to be a plus sign as opposed to a minus sign. All right, so now we have our equations here, and I should say real quick that you may be wondering, why didn't we use a junction rule at point A? That would give you the exact same equation here, so it's no new information. So this is all the information we can extract from the circuit. Now we need to start combining things to get rid of some variables. The first thing I always do is try to use a junction rule to get rid of one of the currents. And so what I'll do is I'll rewrite number 1 as I3 equals I1 minus I2, and I'll use that to get rid of I3 in this equation. So if I plug this in here, that'll give us epsilon 2 plus I2 R2 minus, and then I'll plug in this quantity here for I3. Okay, so now we have two equations. Let me just rewrite this as 3. Well, I'll just say this is 3. So we have two equations. We have this equation number 3, and then this equation number 2. And we have two unknown variables here, which are I1 and I2, so we have to solve for one of those. Which one should we solve for? Well, if you look at what we're looking for the voltage at point B, and we know the voltage at point A. They're directly connected by this branch, so if we know the voltage of this resistor, we can find out the voltage at point B pretty easily, which means we need to know the current at I2. So I'll solve for I1 and get rid of that. So what you can do here is solve this guy for I1, which gives us the following quantity, epsilon 2 plus I2 times R2 plus R3. And then the entire thing is divided by R3. And so you have an expression for I1. Plugging that into this equation will give us only one equation where the unknown variable is I2. So, and because we know all the other constants, we can solve for that numerically. So go ahead and do that. Take a minute now if you need to and pause the video. So plugging in this equation into equation 2, you should arrive at this expression right here for I2. And then all these numbers are known. You can plug those values in and get an actual numerical answer. And what you should find is that the current through this branch of the circuit is about 5.54 milliamps. And we get a negative answer. And what that indicates is that the arrow we originally drew was incorrectly drawn. The current should have been going upward, which is fine. We just got a negative answer to show that to us. And so what's really happening in the circuit is that the current is flowing like this, and this branch is flowing here, but then flowing up through there as well. Now let's answer the question being asked, which was, what is the voltage at point B? We know the voltage at point A is 0 because it's grounded. And now we know the current across this branch, and we know its resistance, so we can find the voltage drop across that resistor. So carrying that out, we find that the voltage drop across resistor 2 equals the current times the resistance. And so the resistance of that resistor is 100 ohms. Multiplied by that, you should get 0.545 volts. And just to check the sign on this, this is 0 volts right here because it's grounded. We know the current flows upward, and current always flows from high voltage to low voltage. So we know that this must be a lower voltage at point B than it is at point A. So if this is 0, we should get a negative number, which is indicated by the sign, so that is correct. So the voltage at point B is 0 minus the voltage change, which is, of course, minus 0.545 volts. And that is a voltage at point B, which is what we're asked to find. So let's go ahead and summarize what we've done here. We first indicated all the current directions for each branch of the circuit, which was our choice. We then drew loops in the circuit and applied Kirchoff's laws for the currents and the voltages to find 3 different equations. Algebraically, we combined the 3 equations to find one of the currents, and then we used that current and that resistance to find the potential at point B. So that's it for this problem. Thanks for watching, and if you have any comments or questions, please leave them on the link next to the video, and we'll see you guys next time.